Okay, so this week's topic continues on what we learned last week when we talked about linear kinetics. The explanations for the causes of motion that we'll talk about this week, they don't rely on Newton's laws of motion, but rather on the relationships between work, power, and energy. So by the end of this first lecture, we're just going to focus on learning about work. Out of all the definitions for work, the dictionary actually takes up half a page to describe all of the definitions. But in mechanics, work is the product of force and the amount of displacement in the direction of that force. So, in other words, it's the means by which energy is transferred from one object or one system to another. And mathematically, it's expressed as U equals force times displacement. So U equals F times D. And U is work here. Okay, so because work is the product of force and displacement, the units for work are units of force times units of length, typically expressed as Newton meters. But in the international system of units, the joule, which is just abbreviated here by the letter J, it is the unit of measurement for work. So you can think of 1 joule as the equivalent of 1 Newton meter. So to determine the amount of work that's done on an object, we need to know 3 things. We need to know the average force exerted on the object. We need to know the direction of this force, and we need to know the displacement of the object along the line of action of the force during the time that the force is acting on the object. So here's an example. A discus thrower exerts an average force of 1,000 newtons against the discus while the discus moves through a displacement of 0.6 meters in the direction of the force. How much work did the discus thrower do on the discus? So you can pause the video and try to solve that for yourself here if you know the average force and the displacement and you're looking for work. If we just plug in those numbers into our work equation, we get 1,000 newtons times 0.6 meters. That's the displacement. So we see that the discus thrower did 600 Newton meters or 600 joules of work on the discus. So let's try an example that's a little bit more complex. We have this weightlifter that bench presses 1,000 Newton barbell. So this is the 1,000 Newton barbell here. He begins the lift with his arms extended and the barbell 75 centimeters above his chest. So this is the beginning of the lift. The lifter then lowers the barbell and stops it when it's 5 centimeters above his chest. He pauses and then he lifts the barbell upwards away from his chest and back to that original starting position of 75 centimeters above his chest. The average force exerted on the barbell by the lifter while lowering the weight is 1,000 newtons upwards. The average force exerted by the lifter while raising the weight is also 1,000 newtons upwards. So that means that the average force exerted on the barbell by the lifter is 1,000 newtons for the whole lift. The question is, how much work did the lifter do on the barbell from the start until the finish of the lift? So feel free, and actually I encourage you to try solving this question on your own before moving to the next slide or before continuing the video. Okay, so if we look at our work equation, we need the force and we need the displacement. We know that the average force is 1,000 newtons. So what is the displacement? Technically, the displacement is 0 centimeters because the barbell comes back to its starting position at the end. But if we just plug that into our equation, we get work of 0 joules, which doesn't make sense because there had to be some sort of work exerted on the barbell for it to move. So that's a problem. As the lifter, I would be pretty upset if someone told me I did no work in this entire motion. The thing is that the lifter did burn some calories lifting the barbell. So physiologically, there was some sort of work done. However, mechanically speaking, there was no work done on the barbell because it's in the same position when the lift ended as when it started. So instead of looking at the work over the entire movement, we need to break it down into phases. And we'll call them, in this case, the lowering phase, so from here to here, and then the raising phase from here to here. So we'll start by solving the work done in the raising phase. So the displacement of the barbell during its raising was 0.75 meters, that's the final position, minus 0.05 meters, that's the initial position, right? So plugging in those numbers up here for the displacement, we get a total displacement of 0.7 meters, and that's positive because the displacement is upwards. So the work done during the raising phase is 700 joules of work. Now for the lowering phase, the displacement of the barbell during the lowering phase was 0.05 meters minus 0.75 meters, right? Because this is our final position for the lowering phase. So the displacement in total was negative 0.7 meters for the lowering phase, which gives us our work of negative 700 joules. So as we can see here, mechanical work is negative if the force that's acting on an object, so this 1,000 newtons, is in the opposite direction of the motion or the displacement of the object. So now it makes more sense why there was no mechanical work done on the barbell, because the work during the lowering phase, negative 700 joules, and the work during the raising phase is 700 joules, which gives us a total work of 0 joules, right? If you just add these two numbers together, you get 0. So work can be positive or negative. Positive work is done by a force acting on an object if the object is displaced in the same direction as the force. So for example, a pitcher does positive work against a baseball when throwing it. A weightlifter does positive work when lifting or raising a weight, as we just saw with the bench press. And a high jumper does positive work when they're jumping off the ground. Now, negative work is done by a force acting on an object when the object is displaced in the opposite direction of the force acting on it. So a catcher does negative work against the baseball when they're catching it. A weightlifter does negative work against a weight when they're lowering it, like we saw. And friction does negative work on a skier that's sliding down a hill. So the last thing that we need to know about work is that our muscles also do mechanical work. So when a muscle contracts, it pulls on its points of attachment. So positive work is done by a muscle when it contracts and its points of attachment move in the direction of the muscle force that's pulling on them. So the force and the displacement are in the same direction. The muscles shorten and the muscle contraction is called a concentric contraction. So that's this first example here. The muscles are shortening, the force and the direction of motion are the same, so we have positive work when we're talking about a concentric contraction. Negative work is done by a muscle when it contracts and its points of attachment move in the opposite direction of the muscle force that's pulling on them. So if the muscle, this is the muscle that we're looking at here, these are the points of attachment on either end, and they're lengthening as the person is putting the weight down or lowering the weight, right? Going from this position to this position, this muscle is actually lengthening. So we call that an eccentric contraction, and it's an example of negative work. So not all muscle contractions produce mechanical work. This would occur when a muscle contracts and its points of attachment don't move relative to each other. So the displacement at the point of muscle attachment is 0. the length of the muscle remains unchanged, and the muscle contraction is what we call an isometric contraction. So picture yourself just holding this 10-pound weight in the air. You're producing a force to be able to just keep that weight up there, but your muscle is not actually lengthening or shortening. It's just staying the same. So that's called an isometric contraction. And because there's no displacement, there's no work, no mechanical work being done. Okay, that's it for this first lecture video. All we did was learn about work, but it's very important. So stay tuned for the next video where we're going to focus on energy.